Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Karfitri Hisham.
And my name is Kevin Lowell Bilian. So in this assignment, I'll be going to present for the introduction first. So okay. So for the introduction, we know that most modern microwave filters are designed using the insertion loss method, where the amplitude response is approximated using network synthesis technique for microwave distributed circuit elements. And also the microwave distributed circuit elements follow a four-step procedure, and also determining filter specification, designing a low pass prototype filters, scaling and transforming the filters, and implementing are the procedure. Okay, so for the low insertion loss and band pass filters are preferred for frequency multiplexing in satellite communications. Then compact and inexpensive low pass filters are made from coaxial line sections of varying diameter, and active microwave device or field effect transistor are used to provide filters with gain or tunable response characteristic. Okay, that's all for the introduction. Okay, for the theory of low pass filters, we know that low pass filters pass the low frequency signals and reject the high frequency ones. And then the frequency bandwidth, ripples, insertion loss, and voltage standing wave ratio are specified. And the cutoff frequencies for RF low pass filter is specified. Okay, next is the high pass filter. The high pass filter pass the high frequency signals and reject the low frequency signals. It is the same that the frequency bandwidth, ripple insertion loss, and voltage standing wave ratio are also specified, and the cutoff for the RF high pass filter is specified. Okay, next is the band pass. Uh, As for the band pass filter, it is it pass through the signal from a specific frequency band and reject out of band signals. The RF band pass filters include the SAW, crystal, and cavity filters. The frequency, bandwidth, ripples, insertion loss, and voltage standing wave ratio are the band pass filter specification. So the next one is the lump design. Uh, as we know that the estimate value of capacitance and inductance in lump element filters were to determine using the insertion loss technique, and the insertion loss method includes network synthesis technique to provide the filter's desired frequency response. Okay, the next one is the distributed element filter design. So for the design use, no. Okay. So for the distributed element filter design, it use no discrete inductor, capacitance, and resistors, and then it can have tighter tolerance, making it for better high frequency applications. And to simply put it, a transmission line is a two conductor structure, and a waveguide is a single conductor with a hollow metal tube that distribute inductance and capacitance. So the figure 12 shows a ladder of architecture lump element prototype with the step impedance filter that can be used to make a low pass filter. The filter is made up of alternating part with high and low impedance that correspond to the shunt capacitors and series inductor. Okay, so for the next one is the design. So I'll give it to Khairul.
Okay, thank you, Kevin. Now I will explain a little bit about the realization, or in other words, design. Okay, first here is the low pass filter design. In lump design, as you can see here, we have designed the low pass filter circuit. It consists of capacitor and also inductor. The parameter that we use is 0 gigahertz for start, 5 gigahertz for stop and 1 megahertz for step. And for the low pass filter, which is in distributed design, here is the circuit that we already create, that we already construct. We also use the S parameter for start is 0 gigahertz, and stop is 5 gigahertz, and step is 1 megahertz. The M sub we use as follows in the question given. And this is the low pass filter after it been distributed, and this is the layout form of the circuit, and this is the band pass filter in LAM design. This is the T network band pass filter that we had created. And the parameters also we use 0 gigahertz for start, 5 gigahertz for stop, and 1 megahertz for step. And now we go to the results. This is the result of the low pass filter. The question given for us is the frequency, the cutoff frequency is 3.1 gigahertz. And the insertion loss is 22 dB at 6.2 gigahertz. The 6.2 gigahertz is the frequency, and the ripple is maximally flat, or in other words, it is zero. Okay, here you can see that we find the omega value and also omega c value, and then after we calculate it, we can get the n value, which is 4, is the uh, value for the n based on the table. Okay, G1, G2, G3, and G4. The R naught or RS, we assume it as 50 ohm. Okay, this is the calculation to find the value for inductor and capacitor. Okay, this is the maximally flat graph. Here we can find the value for n. Okay, and this is the maximally flat table. Here where we got the G's value. Here you can see G1, G2, G3, and G4, also G5 value. Okay, but we only take the G1 until G4 value. And this is the constructed circuit that I have already told you about. Okay, this is the T network low pass filter circuit, as you can see here. And this is the graph output from the low pass filter. And then after that, we transform it by using the Richards transformation. And here is the schematic that we only sketch it inside the paper. Okay, here you can see the calculation value. Okay, and then we go to the Kuroda identity. After the Richards transformation have been made, we use the Kuroda identity to find the distributed circuit. Okay, here you can see we also use a sketch in this Kuroda identity part. Okay, and here is the circuit that I've told you before in the design. Okay, this is the before tuning circuit. As you can see here, the value is based on the LCalC, which is the tools we use in the ADS application. And this is the before tuning graph output. And after tuning, there is some changes at the length where the instruction asks us to change the length to find a better graph. Okay, this is the tuning parameter which we have been adjust. Okay, and this is the graph output when we adjust the parameter of the tuning. Okay, and uh, here is the circuit where we want to make a layout of for the distributed circuit, as you can see here. Okay, now we go to the bandpass filters part. For the bandpass filter part, the question gives us 3.1 gigahertz of center frequency, which is F node, 3 dB ripple, 350 megahertz bandwidth, and also uh, the value of n is 4. Okay, here's all the value of n's, which is G1, G2, G3, and G4. This is the T network bandpass filter which we have created. This is the calculation to find out the all the value for F1, F2, omega node, omega 1, omega 2. Okay, and this is we refer the table at 3 dB ripple table to find out the G's value. Here you can see G1, G2, G3, G4, and G5, but we only take G1 until G4. Okay, this is the T network low pass filter prototype. Before we want to create a band pass filter, we must do this first. Okay, this is the calculation part and also the value that we get for L1 until C4. This is the circuit prototype, T network low pass filter circuit prototype. And this is the calculation for series part, and this is the calculation for shunt part, as you can see here. And this is the band pass filter circuit that we've already created, and we also use the same as the low pass filter as parameter. Okay, and this is the graph output for our band pass filter circuit. Okay, now I pass it back to Kevin for discussion and conclusion.
Okay, thank you, Khairul. So for the discussion, we know that the lump design circle is determined by using the insertion loss technique, and the number of orders for the filter is determined by utilizing a maximally flat outer tension graph and a table of ripple elements values. Then after that, for the numbers of order that is n equals to 4 and value of G1 until G4 can be determined by referring to the elements value table. So the capacitance and inductance is then can be calculated by using the capacitors C case and L case formulas and the elements value. So for the task 2, we we are asked to develop a lump circuit for a band pass filter. So the first thing we need to is to discover the F1 and F2 with the provided center frequency, and then the value of G1 through G4 were obtained from the 3 dB equal ripples table starting with the n equals to 4. Then after that, we can determine the shunt capacitors and series inductor values using the formula provided and get the desired result. So that's all for the discussion. Okay, for the conclusion, we know that the low pass filter and band pass filter were designed and similar and also analyzed using lump and distributed elements. So the simulation result shows that the filters operate perfectly at the designed frequency. So that's all from us. Thank you very much.
Thank you very much.